Okay. So what we did, how we ended class on Tuesday was I went through all of the ways that we can put an electrophile on a benzene ring. So I'm going to just kind of recap that up top here. So there's your benzene. And so you can acylate a ring. You can alkylate a ring. You can nitrate a ring. You can brominate a ring. And you can chlorinate. All right, so just take a minute and draw the different mono-substituted benzenes that you would get.
It dawned on me that in the last semester we didn't see so many elements. It's just surprising seeing iron again.
Oh,
Iron, aluminum.
We didn't work with metals very much. All right, so to acylate, you put that R group on with the carbonyl. To alkylate, you just put an R group on. To nitrate, you get a nitro group on. To brominate, you get a Br group, and to chlorinate, you get a chlorine. So that's just how you monofunctionalize a ring. And yesterday in recitation, I kind of showed you what happens when we put something on the ring, and then we can then modify that, right? So let's just go through that example. Do you guys need this still? Are we still writing this down? Sorry. So just like when I'm writing on the board, you got to tell me if I can't scroll, okay? Because I didn't try and remember to look up at you guys, but just, stop me. All right. Can I roll it up? Yes. All right. So yesterday in recitation, we did an example like this, where I gave you a benzene ring. I had you acylate it. And then you had to draw that product. And then I gave you another reaction. Okay, this was an old reaction where you then converted this into an alcohol. All right, so we're kind of now at the point too, where I'm going to post a list of the old reactions that you need to know from last semester. Okay. Just to tell you right now, right, you have to make sure, right, that you know the oxidations and the reductions that we went through, because those are just we're going to just see them when we do the alcohol chapter and the carbonyl chapter, okay, and the carboxylic acid chapter. So they'll actually be listed in the textbook as well, okay, when we go through those chapters. So those are two definitely old reactions that you need to know. Electrophilic addition to an alkene. Okay, that's where we did that HX or the X2 addition. Okay. And also know your elimination reactions. All right, so how to make alkenes. We saw, just to refresh your memory, okay, I did it in context of the benzylic carbon. Okay, but you could do NBS, which is that allylic bromination. And again, just to remind you, we oxidized. This was in chapter 17, the benzylic carbon. Okay. All right, so not only now are we going to have to worry about doing chemistry on what we attach to a benzene ring, but now we're also going to work on putting substituents, okay, more than one. So it's not just doing a mono electrophilic addition, but what happens if we want to put more than one functional group on a benzene, okay? So we are going to look at activation of benzene or an aromatic ring, because I want to do these reactions with you with those heterocycles. Right, and we're going to look at directing effects. All right, so when you have benzene or something that's aromatic, and you want to do electrophilic aromatic substitution. Okay. Once you put a substituent on the ring, it changes the reactivity, okay, to additional electrophilic aromatic substitution. Okay, so for example, if you just have benzene compared to toluene, so this is benzene, you do not have to know the names. Oh, all right, you have to know the name of benzene. And this is toluene. Okay. These two molecules, right, have different levels of reactivity to electrophilic aromatic substitution. Toluene is actually going to be more reactive than benzene. And the reason for this is the nature, okay, of that methyl group. Okay. So if you remember when we went through this mechanism, and you have to know this mechanism. You have the intermediate. What charge is on the intermediate? Is it positively charged or negatively charged? With electrophilic aromatic substitution. So we're adding an electrophile to the ring. What kind of charge are we getting on that intermediate? Positive, right? So when we added a nucleophile to the ring, right, we got a negative charge on the ring. When we add an electrophile to the ring, we get a positive charge in the intermediate, okay? So the intermediate is positively charged in your electrophilic aromatic substitution. So when you put an electron donating group on the ring. You activate the ring, right? If you put an electron withdrawing group on the ring, you deactivate the ring. So remember your electron donating groups. You have your alkyl groups. And then you are going to have your atoms with lone pairs. Okay. And so you're looking at oxygen and nitrogen and sulfur. Okay. Your deactivating groups, those are your electron withdrawing groups. Okay, so they are going to pull electrons toward them. So you're looking at anything that's got a partial positive or full positive charge. Okay. Your carbonyls, you have a partial positive. Your nitro group, you have a full positive on that nitrogen. Here, actually, let me draw it out so that we get used to seeing that nitro group. Your cyano group, you're going to have a partial positive on that carbon. The other one that we have not gone through, okay, and there is going to be another, like, I don't want to say exception, but something to keep in mind, okay, are your halogens, okay? So your halogens, okay, they actually can go both ways, all right? And we're going to see this kind of in your, when we look at the directing effects, okay? Actually, you know what I'm going to do? I'm going to put the halogens. I'm going to put the halogens here. Okay, this is what we'll do. I'll make a separate category for the halogens. Bless you. All right. So I'm going to put the halogens here as a separate bullet point. Okay. So your electron donating groups are activating. Your electron withdrawing groups are deactivating. Your halogens, and I've said this to some of you who have come to see me for office hours, you have these lone pairs on your halogens, okay? So your halogens are actually weakly electron donating groups because of the halogens there. I mean, because of the lone pairs there, I'm sorry. Right. However, they are deactivating in electrophilic aromatic substitution. Okay. So we are going to see that this electron donating group effect, right, will come into play when we look at the directing effects. But from an activation deactivating, because the halogens are electronegative, I can spell, okay, and they have a high affinity for electrons. They are going to deactivate a ring towards electrophilic aromatic substitution. Okay. So if I have a ring Well, if I give you two possibilities. And I say, which will react faster with HNO3 and H2SO4. A or B? Which one will react faster by nitration? Which ring has an activator and which ring has a deactivator? AJ.
Yes, deactivated.
Right. Okay, so A is going to react faster because the OCH3 group is an activator. The BR group is a deactivator. So this is going to react slower. All right, so that's your activation and your deactivation. Gabrielle. Okay, so when we've evaluated like in all of our reactions that we've looked at, right? I've given you substrates. So let's just take SN1, right? So in each reaction that I've gone through, and we've discussed the mechanism, right? We looked at the slow step was formation of the carbocation. So in order to react faster by SN1, you make the more stable carbocation. Right, so if I give you a series of substrates, and I say, rank the order of reactivity by SN1. All right, from slowest to fastest. Which one is going to have the slowest rate of SN1 reaction? C. Which one's going to have the second slowest? A. Which one's going to be the fastest? B, right? So I can do this and explicitly say to you SN1, or I could give you reagents. I could have given you a weak nucleophile. Okay. So we're at the stage where you have to be able to recognize, if I give you reagents, how they are going to react, by what mechanism are they going to react with. Okay. So when I say which one's going to have the fastest rate of EAS, you have to understand that mechanism of electrophilic aromatic substitution, or I can just give you the reagents, right? If I give you nitric acid and sulfuric acid, you need to know that that reacts by EAS.
So when you say it activates it, it's gonna go through EAS and if it deactivates it, it won't.
It will still do it, but at a slower rate.
Oh,
Okay. So same thing, we did this with our dienes, right? I said to you which diene, depending upon if you put a substituent on it, when we were looking at Diels-Alder. We did this in recitation. So if I say to you, so which one's faster? And I gave you those two dienes. All right, this is where you need to remember the conformational flexibility and that this one can rotate. Okay, and that the S cis is less stable than the S trans. So that this one reacts faster because it can't rotate. It's already fixed in S cis. Both of them have electron donating groups on them, right? You have those two methoxy groups, so that can't be what distinguishes their rate of reactivity. So one of the things that I recommend doing, and I did this actually, so I did this in office hours yesterday, right? Go through, I'll do this with the Diels-Alder reaction for you now, right? But what you should do, particularly if you look at the modules, I'm not going to do those study guides that I did last semester. I'm putting them at the end of the weekly module. Like, this is what you need to know. So for your studying and going through things, take each of those bullet points and make sure you understand them, okay? So like with the Diels-Alder reaction, you can make checklists, okay? The first thing that you need to look at, okay, is you need to maintain the stereochemistry, okay, of the diene and the dienophile, meaning you have to maintain that E and Z. You need to be in the S cis conformation for the diene. So that's the first step when you're trying to figure out what the product's going to look like for a Diels-Alder reaction. The next thing that you're going to look at is that regiochemistry. If you have a substituent on C1 of the diene, then on the product, that cyclohexene, you're going to have that 1-2 relationship, okay, where it's C1 and C6, so that the electron donating group and the electron withdrawing group on the dienophile are next to each other. This is diene, okay. Then, right, we're going to look at, okay, endo and exo, right? You need to remember that endo is preferred if possible. And with that endo and exo, if this is your diene, right, that electron withdrawing group on the dienophile, it's pointing towards the diene. That's your endo. For exo, it's pointing away. And that's your exo. But notice the hierarchy that I'm doing this list, right? You only get endo if you meet those first two criteria, then we can have the endo being preferred. And then finally, we have the stereochemistry, which we talked about. where I made that imaginary line. And what I'm saying to you now, and I think you should just take this convention, right? It essentially doesn't matter if the left side is up and the right side is down and vice versa. I just think to keep in consistency with the endo formation, particularly when you're making the bicyclics, that you make the left side down and the right side up. So that this is down, 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 down. Up, 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 up. And again, you're just looking at C1, C4 of the diene, and C5 and C6 of the dienophile. Okay. And it's always that plus the enantiomer. If you keep the left side down, it will just make it easier for the endo products again when you have that bicyclic. And when I'm talking about the bicyclics, I'm talking about the case when you have the diene like this, where you're going to get some type of bridgehead carbon. Okay. That's endo because the CN is right. And if you look, right, that CN is essentially down. All right. So it just helps keep that clear because it needs to be opposite of that bridge. Okay. So you should do this. You should kind of lay this plan, this framework out for each of the mechanisms that we go through. All right. So with EAS, you have to look at these activating and deactivating effects. Then what we also have to look at is now the directing effects, okay? And so what I mean by directing effects as soon as we put a substituent on this ring, and we tried to do another electrophilic aromatic substitution. So we're going to add more to the ring. Okay. We have 3 possible products. The bromine can be ortho to the methyl group. The bromine can be meta to the methyl group, or the bromine can be para to the methyl group. Okay, those are your 3 possibilities. The other meta and ortho positions on the top side of the ring are equivalent to ortho and meta on the bottom side of the ring. Okay, meaning those 2 positions are equivalent. And then those 2 positions are equivalent. Okay. All right, so we're going to look at the resonance structures to figure out which ones are going to dominate. Okay, so here's my ring. Here's my electrophile. I'm going to do the ortho one first. All right, so this is a mechanism, again, you need to know. So the pi electrons go after the bromine. And I told you, you just really need to know it from this point where you have the electrophile. All right, your bromine, if it's adding ortho, it's adding adjacent. All right, remember there is a hydrogen there on that carbon. Right, that becomes electron deficient. Now let's delocalize this charge around the ring. Okay. So I have my positive charge go here, here, and then it ends up on the carbon, all right, with that electron donating group. When you have an electron donating group adjacent to a positive charge, it's stabilizing. It's stabilizing because it's pushing electrons toward the positive and decreasing the magnitude of the positive charge. Right? The whole idea is you don't want charges. You want things to be neutral, or you want your charges to be spread out. So if we can push some electron density into that charge, okay, we make a more stable, happy, positive charge. All right. Now we're going to do this for the meta position. So again, my pi electrons go after the bromine. And so now my bromine adds meta to that methyl group. So then I get the positive charge ortho. Okay. And so now what we're going to do is, again, let's delocalize this charge. So I can delocalize the charge, right? I still have 3 resonance structures, but I don't have the case now, right, where I have my electron donating group directly adjacent to the positive charge. Okay, so you still have resonance. But the extra stabilization of the electron donating group is not there. And again, understand this pushing, that's that inductive effect. And if you recall from our discussion of the inductive effect, it's distance dependent. All right, so again, in this second case where the bromine is adding meta to the electron donating group, all right, you're further away. The charge is further away. So induction is weaker. Okay. All right, I'm going to start you off on the para substituted one. I want you to try and draw the other 2 resonance structures that you get. So we have the benzene ring again with the methyl group.
Dr. Stouter,
Mhm.
the second point where it says charges further, what does it say after that?
So induction is weaker. All right, so the pi electrons go after the bromine. The bromine has to add para to that methyl group. Okay, so that is the first structure that you get. Draw the other two resonance structures that are going to occur for this type of substitution. All right. So we can see that the charge again is close to that electron donating group. All right, so we get the charge here, here, and here. And again, you're going to have this extra stabilization. All right, because the charge is close to the electron donating group. All right, so you have a stronger inductive effect. Okay. So we are going to have ortho-para directors, and then we are also going to have meta directors. Okay. Now, based upon what I just did, what type of group do you think is an ortho-para director? An electron donating group or an electron withdrawing group? Electron donating groups, okay? So your electron donating groups are ortho-para directors. You get extra resonance stabilization by the inductive effect. Okay. So your electron donating groups, we're going to have our alkyl groups. We are going to have anything with that lone pair. Okay, so here I'm going to add the halogens. Your oxygen, your nitrogen, your sulfur, and your halogens, okay? The halogens are going to be ortho-para directors, even though they are deactivators. I'm going to add if you have a full positive. All right, we did this yesterday. All right, when we were looking at acidity, it made something less acidic. Okay, so something like a nitrogen. No, wait a minute, that's not right. Sorry, nope, just scratch that. That's your electron withdrawing groups, okay. Sorry, so your halogens there, all right. The other one that I want to add is your pi electrons. So if you have another aryl group, and I'll show you an example. All right, so if you have another aryl group attached to the ring, this is going to be an ortho para director. All right, those pi electrons can be pushed towards the positive charge. Your meta directors are going to be your electron withdrawing groups. So your partial positive or full positive. Okay, again, your carbonyls, there's a partial positive. Your nitro groups, there's a full positive on that nitrogen. So they are going to direct to the meta position. So just to demonstrate this from an example perspective. All right. You need to draw the product or products. So you're going to look at this, right? And when we look here, this, is it an electron withdrawing or an electron donating group? You have a partial positive on that carbonyl. What kind of group is that? Electron donating or electron withdrawing? Withdrawing, okay. So you're going to direct to the meta position. If you look at the example beneath it, okay, you have a lone pair on that nitrogen. Okay, so in both cases, we have amides attached to these benzene rings. In one orientation, it's the carbonyl. In the second orientation, you have the nitrogen attached. So when you have the nitrogen directly attached, is that an electron withdrawing or an electron donating group? It's donating in this orientation. So you have ortho para direction. So now draw the products that you would get for these reactions. So in the first case, meta, second case, ortho, and then para, right? So this is fine when we just have one substituent on the ring. But we have to figure out what to do, right? When you have more than one substituent on the ring. So this is when you have to take into account both the activating and the deactivating effects. Yeah.
So this, it's like on a test,
Mm-hmm.
you have to go both the one on tomorrow, or you just
All right, so if this was multiple choice, it would probably be, you would have like 1, 2, and 3. And then you'd say it's products 2 and 3. Like if I made this one 1, this one 2, and this one 3. Okay, so your choices would be 1, 2, 3, or okay,
Yeah.
something like that. If it was a fill in the box, so look, when I give you a practice, you're gonna see on the part 2s that you have the possibility where it's just fill it in, right? And I only give you one box, I only expect one product, and then I'll let you make that judgment call as to if you want to pick the ortho or the para. Okay. All right. So if we have something like this. And then okay. All right. So here I have an electron donating group. That is an activator and an ortho para director. I have this benzene ring here that's attached. That is an ortho para director. And then I have this here, okay, which is an electron withdrawing group, which is a deactivator and is a meta director. Okay. So the possibilities for reaction are this carbon. We can brominate that carbon. We can brominate that carbon. We can also brominate the 4 carbons on that other benzene ring. Okay. The ring that I'm going to highlight in orange here with the methoxy group is more reactive than the other benzene ring. All right, just by nature of having that methoxy substituent there and the benzene ring there. Okay, I know I didn't put down activation for the benzene ring, right? But again, you can push pi electrons in, so we'll say it's activating. Okay. One ortho position is blocked for that methoxy group. The other is not. And the para position is open. So your products will be this. And that, okay? So you're going to have to take into account, right, these directing effects and activating effects, particularly if you have more than one substituent already on your ring. Okay.
Wait, why did you pick those two again?
All right, so I said the methoxy group, that OCH3 group, is an electron donating group and it's an activator. The benzene ring, okay, and it's an ortho para director, right? The benzene ring, right? It's weakly activating in that you can push electrons in because of the pi bonds, and it's an ortho para director. The carbonyl that's highlighted in red is an electron withdrawing group and it's a deactivator. So it makes the ring less reactive and it's a meta director. Because you have those two activators, right? The ring in orange will be what reacts, right? So ortho, all right, is here and para is here. Okay. All right, we're gonna do it. I want to just give you a couple more things to consider. Well, actually, we'll do this first. Let's do a synthesis example. So you have benzene. So this is a synthesis. All right, so you have benzene, and that's the product you want to make. You want to put an acyl group on, and you want to put a chlorine on. So if we do a retrosynthetic analysis, and we look at our product, right, you have a deactivator and a meta director. You have another deactivator, but an ortho para director. What is the relationship between the acyl group and the halogen? Are they ortho to each other, meta to each other, or para to each other? They're meta to each other. Okay, so what did you have to put on first? Right, you have to put on that acyl group first. So that if you were to step this back, the last step would be chlorination. Okay. Because you have to acylate first. Because it will direct the chlorine to the meta position. If you chlorinate first, then the acyl group, that carbonyl, will be para and ortho to it. Okay, so this is another example of where you have to take stock right, of what's on your ring. A couple of more things that I want to do before we do another example. We can change groups into activators and deactivators, or meta directors and para directors. So 2 reactions that we have to be aware of. If you have a nitro group, okay, which is deactivating and meta directing, if we take that nitro group and reduce it, because remember, a reduction is decreasing the oxygen content and or increasing hydrogen. To an NH2 group, we have now put an activator on the ring and an orthopara director. Okay. So you don't know, all right, the only way you would know how to put an amine on the ring, right, would be to do your nucleophilic aromatic substitution. So if you don't have the ability to chlorinate and you don't have a strong nucleophile, but you can nitrate, then you can reduce that nitro group to an NH2 group. The other thing that we can do, and I don't feel like I don't know if we did this last semester. If you have a ketone, okay, or an aldehyde, it does not have to be attached to an aromatic ring. So this applies to all. If you add N2H4 and KOH, this is called a Wolff-Kishner reduction. You make an alkane, okay? So again, we've taken something that's deactivating and meta directing, and now made something that's activating and orthopara directing, okay? So that's also something to keep in mind. So we're gonna do one more synthesis, and then I think I'll get a mechanism. I don't know if I'll get a mechanism problem. All right. This is going to involve a combination of NAS and EAS. Right. So take a few minutes and work that out. I'll give you a hint. You don't know how to put that on the ring by EAS. Okay, that you have to get on by substituting a CL using NAS. All right, what's the relationship? What are those, the nitro groups? What's the relationship of them to that methoxy substituent? Right, they're ortho and para. So you had to do the nitration last, right? Because that methoxy group is activating and it's an ortho para director. All right, I'm gonna put excess here so that we know that we got every position. Right. Now that methoxy group, you can put that methoxy group on by doing nucleophilic aromatic substitution. Okay. And then you got that chlorine on by halogenating the ring. Now, if some of you, all right, let me just write this in the forward direction. So first step is Cl2 and FeCl3. And then you can do the nucleophilic aromatic substitution, and this would be by that benzyne, so it would be elimination addition, which I don't need you to add, okay, but I'm just telling you, right? And then HNO3 with H2SO4, and so you could do an excess of it. Okay. Now, if some of you thought, all right, to put the chlorine on and then those nitro groups on, right? Because the chlorine is an ortho para director. So say, like some of you said, all right, let's chlorinate. Or some of you could just not have thought of this either, and that's fine. Chlorinate, and then do the HNO3, H2SO4. Okay. I would accept this because then it would be, I could understand in the context of what we've discussed, that you could just then add the methanol, okay? And then you would think it goes by addition, elimination, because of those electron withdrawing groups, right? The reason why this is not the best way is because then you put 3 strongly deactivating groups on that ring, right? You just, I understand that you would be then doing a different type of reaction, right? But you are really, no, that's okay. I step that back. I go back from that. You could do it that way too, because it's going by nucleophilic aromatic substitution here. Okay, so this is the second route that you could do that with. Okay, so either one. All right, so this is route 2 that you could do, where you did EIS first and then NAS. Okay, because again, remember, these are those electron withdrawing groups. Or you could have done EAS, NAS, EAS. Okay, so this would be route 1. Make it a little bit smaller, then I can get everything on the screen. So those are 2 possibilities for synthesis. So I want you to realize you can do synthesis, multiple ways. But you should absolutely add these reactions to a roadmap. Okay. I highly recommend making a roadmap because I'm most likely going to give you extra credit if you submit another roadmap. Okay, because it's just a good exercise to do. All right, the last thing I want to look at is just showing you from a mechanistic perspective if you have an aromatic heterocycle. Okay, so what I want you to do here is first just draw the 3 possible products. I'm going to emphasize here that there is no ortho, para, and meta because we do not have that 6-membered ring. Okay. Does everybody see that I have these three possible positions in orange that I can brominate? And so there are my three possible products. Okay, so now what we're gonna do is we're gonna draw the resonance structures to figure out which one would be the major product and which one would be the minor. So again, you just have to draw the electrophile. So the pi electrons go after the electrophile. I'm going to add the Br to the top carbon. So that means my positive charge is there on the bottom. No, that's not right because I have a methyl group there. 1 second. Let's try this again. All right, I'm going to add the Br to the bottom carbon and put my positive charge there where my methyl group is. Okay, so now resonance. All right, those pi electrons can move over. And then there's my positive charge. I have one more resonance structure, the lone pair. And now the oxygen would be positively charged, okay? Does everybody see how I got those three resonance structures? Yes, no, maybe so. Do we see how I got those, how I moved the electrons? Okay. To react with the other two carbons. So the pi electrons take the Br. All right, so for that, if the Br is adding to the top carbon, all right, the lone pair can come over. And I have that resonance structure where I have a positive charge on the oxygen. Right. That is it. That is all I can do. Right. So there, you need to have some restraint in drawing your resonance structures. I know sometimes we just like to kind of keep going because we think we can, but you need to just understand that sometimes they just stop. Right. And then for that last carbon where the bromine can add, same pi bonds, okay, these ones on the left. So my pi electrons can come over. And then I have one more where the lone pair can come over. I drew it in the wrong spot. 1 second. All right, so there are my three resonance structures. I'm sorry to make it smaller on the screen, but if I were to ask you, Which is the major product? All right, would it come from A, B, or C? AJ, why?
Because the positive charge is closest to the positive group.
Exactly, okay, so if you look, we have, all right, so we can automatically rule out B, right? Because there's only 2 resonance structures. All right, so if the major product's not going to be B, if you look at A and C, you have 3 resonance structures in both cases. It is this first one here that I drew that puts A over the edge. Oh, I should have done it in red, sorry. Okay. Because you have this positive charge here adjacent to that electron donating group. All right, this is the most stabilizing. So if I go back to my 3 products, this is going to be the major. You are going to have to be able to do this. Okay. Okay, so right now I'm envisioning your part 2s. And again, I'll get you a practice test, which will be reflective of the format, but you're going to have electrophilic addition to a diene. You're going to have some type of Diels-Alder and electrophilic addition, sorry, electrophilic substitution mechanism and a synthesis. Okay. I'm going to put the Diels-Alder in parentheses. I might substitute it out for an NMR. I'm not sure yet. We haven't done a ton of NMR, so I don't know if I'm going to just drop it on you for your first exam. I might ease into it because next week when you do the isolation in the lab, you're not going to do NMR right away anyway. So I might just save NMR for the second test. Okay. All right. Thank you, everyone. Have a good weekend. And for those of you, I'll see you in lab. Yes, see you tomorrow.
I'm getting a combination thing figured out.
Okay. All right. Sounds good.